So welcome back to Physics of Music. I'm going to start as usual with a quick review of the last video. And so what we were talking about were these rules for how to predict positions and velocities at future times if we know the positions and velocities of objects at the present time. And so the first important thing was that if we want to know the rate of change of position, well, that is just equal to the velocity. And the second thing is that if we want to know the rate that the velocity is changing at, or the acceleration, what we need to do is look at what are the forces acting on the object, divide the force by the mass, and then that tells you the rate of change of velocity. And then we can use these two results to make our predictions about the future. So here's just a quick summary, a little bit different than the one I gave last time. So suppose we have the current position in some direction I'll call x, and the current velocity in that direction, and we want to predict the positions and velocities after a short time t. So what we do is first think about what are the rates of change for those two quantities. The rate of change of position is velocity. The rate of change of velocity is the force over the mass. We might need to calculate that from the position and the velocity, depending on which forces we have present in our system. Once we have the rates of change, we just multiply those by the amount of time in order to get how much the quantity changes in that time. So the position changes by the velocity times this time. The velocity changes by the force over mass times the time. And then to get the new position and the new velocity after this amount of time, we just add those to the old position and the old velocity. So the new position is x plus vt. The new velocity is v plus f over m times t. And it's important that we take this time to be short enough so that the velocity and the force don't change significantly during that amount of time. So just to change a little bit, and that way these things are going to be accurate. If the velocity is changing too much, you wouldn't know which velocity to multiply by t. And so t should be a short time. And so in order to make predictions a longer amount of time into the future, what you want to do is just repeat this process a bunch of times, and then that will tell you the position and the velocity after whatever amount of time you want. So we had this example last time where we have an object. It's subjected just to one force, which is a drag force. It's a force proportional to the velocity, but in the opposite direction. Okay, and by proportional, I just mean that if velocity doubles, this force doubles. And what we were trying to do is basically just fill in all those quantities. And so just to make sure you got that, it would be worthwhile taking a minute to just think through this question. I've given you already the rate of change of the position, so that's the velocity, 3 meters per second. Just take a minute to figure out what is the rate of change of the velocity at this present time, given all the information above. Okay, well, let's go through that. And so the thing that we're going to need to use is Newton's second law, that the rate of change of velocity is equal to the force divided by the mass. So we know the mass is 2 kilograms, and we know that the force is, in general, in this environment for this question, given by this formula, that it's minus 6 kilograms per second times the velocity. And so what we want to do is just take our velocity, which is currently 3 meters per second, multiply it by minus 6, and that will be the force. So the force is minus 18 newtons. It's a force in the opposite direction to the direction that the object is currently moving. Next, we want to take the force divided by the mass, because that's the rate of change of velocity. And so if I were to do that, we would get minus 18 newtons divided by 2 kilograms, or minus 9 meters per second. So the units always work out to the right units as long as we're using newtons and meters and seconds and kilograms. Then when we calculate this, we're going to get a quantity with the right units, which in this case are meters per second or meters per second squared. Okay, and someone in class asked, like, why is there a square there? How do you know it's meters per second squared for a rate of change of velocity or for an acceleration? And the reason is that what we're going to do is multiply this rate of change by an amount of time, by some number of seconds, and then we want to get a change, a number of the amount by which velocity changes. And so if we have meters per second, and then we multiply by something whose units are seconds, then the answer will then just be meters per second, and that's what we want for a velocity. So let's just have a look at how that works in this example. I've gone back to the previous numbers in the original version of the question. And so you got the current position of 2 meters, the rate of change is 3 meters per second. The change during that time of 0.1 seconds is then the product of the velocity or the rate of change and the time. So that's 0.3 meters. And so the new position is 2.3 meters. The velocity is 3 meters per second. The rate of change is the force over the mass, which for these numbers is minus 0.5 meters per second squared. We multiply by our 0.1 seconds to get the amount that the velocity changes by during that time. And so that is something with the units of velocity. The change is minus 0.05 meters per second. We add that to the original velocity, and now the new velocity is 2.95 meters per second. And so what you would realize is that if you wanted to say, no, what is the position of the velocity after, 10 seconds? Well, that means you would have to repeat this procedure 100 times. And well, that's kind of a real pain, but it is no problem using today's technology. So instead of doing these calculations on a piece of paper with your pencil, you want to just tell a computer to do the calculations. And I just want to give you an example of how that would look. Okay, I'm not really going to get into computer programming in this course, but I just want to show you how easy it is nowadays to tell a computer to do all these calculations. Okay, so let's have a look at this video. And so I wanted to give you an example of how we can use a computer to very quickly and efficiently do the kinds of calculations that we were just trying on our own in order to make predictions about future positions and velocities of an object in a particular environment and subject to particular forces. So it doesn't matter if you have no computer experience, you'll probably understand roughly what's going on. So I'm just telling the computer various things that are the same as the information that we were provided in the problem. So I'm telling the computer the mass of my object is 3, the original position is 2, the original velocity is 3, and that the time step that I want to use is 0.1. And then I'm going to give some commands to do these calculations that we had to do. So the instructions I'm going to give the computer is to calculate this force, and that's going to be equal to minus 0.5 times the velocity. And then I'm going to instruct the computer to change the position by the velocity times the time, since the velocity is the rate of change of position. And we're going to change the velocity by the force divided by the mass, that's our rate of change of velocity, and then times the amount of time that we're taking in each step. And so you see over here that we have the original position and the original velocity. And now if I click these commands, then the computer will carry those out. There we go. And so the new position is 2.3, the new velocity is 2.95. And if I click it again, the computer will carry it out again, and this is the position and velocity after 0.2 seconds, 0.3 seconds, 0.4 seconds, and so forth. Okay. So I could also just decide that I want to figure out what is the position after 3 seconds. So that would be 30 time steps. So I could just tell the computer to repeat this calculation 30 times. And so I set the original position and the original velocity, and I click this, and it repeats it 30 times, and it tells me after 30 repetitions, so that would be 3 seconds, I have position 9.1 and velocity 1.8. And what's really fun is I could actually visualize this very easily using the computer. And so what this programming language, which maybe you've seen before, this is called Scratch. What this is really great for is doing these visualizations. And so what I can do here is, I've already set this up. I'm just going to tell the computer to draw my object that I've chosen down here at this position X on the screen. So when I set this all up, then it draws the ball there. And I'm going to add another one of these commands after this calculation. So it'll calculate the new position, and then it'll draw the ball at the new position. But I don't want to just do that once. I just want it to keep going. Just like actual time, it just keeps going and going. And so I'm going to have the computer just continually draw the ball at its new position, and then do the next calculation, and then draw the ball again. And I am going to tell it to start that when I click the flag. So we're going to go to this full screen view, and so when I click the flag, the computer is going to start calculating all these future positions of the balls, and then draw the ball each time. And so we should be able to then visualize what's happening to this ball as it moves through the fluid with a drag force. So here we go. There it goes. And so you see it started out faster, and then it's slowing down further and further and further and further. And it looks like it has finally stopped in the fluid. And so basically, using these very simple rules for physics and just this knowledge that the drag force is proportional to the velocity, it's some number times the velocity, and it's in the opposite direction as the velocity, we were able to simulate that on a computer and see just how it would behave. Okay, so hopefully that gives you confidence that even though by hand this procedure will be very tedious and time consuming, nowadays this is something that we can do, and we can basically turn our knowledge of the basic rules for physics into practice and simulate physics with particular forces and kind of see what the qualitative behavior is. We could vary things like the strength of this drag force and see what happens, and basically get quantitative predictions about the motion of objects in all sorts of environments. And I just want to mention that in that example, we only had motion in one direction, and we only had to keep track of the x position and the x velocity. But the method, if I had something more complicated, like an object moving in the vertical direction partly and the horizontal direction partly, and we wanted to simulate the physics of that, well, it's actually just the same thing, but once for each direction. So we keep track of the horizontal position, we keep track of the vertical position, the horizontal velocity and the vertical velocity, and then we just look at the horizontal forces and the vertical forces, and we just separately apply those rules to update the positions and the velocities in each direction based on the forces in that direction. And so if we had done that with, say, this simulation of motion of an object in gravity at the Earth, then you would see in the simulation that you get some parabolic trajectory. So it would look like just like the behavior of an actual object. You can do this for multiple objects interacting with each other. And so if I have two objects, like two planets in space, and they're maybe orbiting, or one planet is orbiting the other, or it's a planet orbiting the sun or a moon orbiting the planet, then you can run a simulation taking into account the fact that those planets are exerting gravitational forces on each other. And I will add a link below to such a simulation. And it will accurately predict for Newton's law of gravity, for example, where you have forces that are proportional to the masses of the two objects and that are decreasing with the distance, in the way that if you double the distance, then the force decreases by a factor of 4. So that's kind of Newton's law of gravity. And if you simulate that, it gives rise exactly to the circular and elliptical trajectories of objects orbiting other objects. Okay. And you could do this not just for two objects, you could do simulations for many, many objects now because our computers are extremely powerful. And I wanted to leave you with a particular simulation that you could go and watch. I'll have the link below, which is a simulation of the formation of our galaxy. And so this is keeping track of like billions of, probably not as many stars as there actually are, but basically billions of objects, and taking into account the forces between those and just seeing how they would interact with each other and how that system would evolve with time. And you see things collapse, and you see that after a while, by the end of the video, you have something that looks very much like we think the Milky Way galaxy looks like. So this procedure of simulation using computers is very powerful. And the main thing that I want to get across is that the underlying physics is this extremely simple set of rules that are captured by the definition of velocity and Newton's second law, which tells us how the velocities will change in response to forces.